So I will record here. So we keep some copy here. So step number 1 is obtain desired curve equation, and s squared 2 omega s plus omega squared is equal to 0, right? Adam, can you hear me, Adam? Adam, can you hear me?
Yes, I can hear you.
Awesome, great, perfect. So I leave this one here. All right. So we know this is curve equation, right? Jackson coming here. We know these are correct equations. And as long as we know eta omega s, and welcome Jackson. Jackson, we just talked about the exam, right? Next Wednesday, okay? And right. So we know this our goal here, we want to calculate this curve equation. We also know that as long as we able to calculate eta omega n, right? So we can calculate this desired curve equation, right? So the question is how we can do multiple poles. And we know these 2 poles here, right? For a higher order system, there's multiple poles. There's S1, S2, S3, S4, S5, so on and so forth. For a higher order system, right, we just plug the pole here, and multiply original here. So we get higher order poles, right? Sorry, higher order curve equations. So we know eta is damping ratio, omega natural frequency, right? So as long as we plug a number here and we plug pole here, we can calculate any degree of freedom, right? Any order of any just high order, right? 3 order, 4th order, 5th order, right? So on and so forth. So the question is, how we can get eta omega n, right? So eta omega n we can get through this following here. So given control formulation or given any control like corrections, like your journal, for example, your class project. So you should know like your overshoot. That's your desire, okay? Well, how much overshoot you want? You tell me, right? You tell me like 5%, 10%, 15%, right? Great. And you also should know your settling time. So this is 2 important metric. Is our design. That's our design goal here. You need to know this design goal is not from you, right? A control engineer like you, probably not from yourself, rather from your users. Because we are a senior student right now, right? So we're graduating. So we want to work for our companies. So we want to know develop some real stuff. So like you work for a company, your boss say, look, like Adam, or like Zubin, right? Or like Ibrahim, So look, I want you to design something system, okay? Like a PLC system, right? I want to design some like a manufacturing system. And so all the parts, right? All the stuff, right? I mean, together is in motion. The overshoot cannot be exceeding this limit. And the session time must not be exceeding the limit as well. So you have the 2 important metrics. You're given the 2 important metrics by a boss or by your users. For example, you start a consulting company. Your consulting firm and your client tell you this metric. So based on the overshoot at a certain time, you can calculate eta and omega n, which is very feasible. Why? Because this overshoot is a function of eta, right? So this eta is given this formula here, okay? And you know eta based on overshoot, you calculate omega n based on this settling time. So that's actually the purpose. Remember we reviewed the time response in the beginning of the semester. Let's review the purpose like this. Because that's the first step of doing any control project. You base on overshoot, You based on your certain time, you can calculate eta omega n. Eta is Nathan come back. So eta is again, eta is what is eta here? Anyone know? You can type, you can speak. What's eta? Again, one more time, eta?
Damping ratio.
Alrighty, perfect, perfect. So how about omega n? Omega n here.
Natural frequency.
Perfect. See, we did the lab, right? And we only focus on important things in this stuff, okay? We actually did the entire lab for this. Remember, calculate natural frequency, right? The Joule, right? So very crucial. You have the natural frequency. This is a real starting point doing any control project, even including PID. Of course, your PID probably doesn't care this stuff. Why? Because PID is modulus. Again, let me type it. PID is modulus. And this is called full state feedback. Is modeled. Of course, PID modulus, right, is less mathematical rigor. And the full state feedback also called pole placement. Full state feedback is actually an academic term. It has a nickname called pole placement. And you can Google in MATLAB, right? There's a lot of example code, okay? So, this was modeled, of course, a little bit harder, okay, a little harder. PID is less challenging. I mean, so here in our class, I don't think we have enough time to implementing full state feedback for your journal, okay? I mean, you can try if you're interested, okay? And that's a very demanding task. However, we do simulation here, okay? I mean, I don't want to make things super difficult for you. I mean, because full state feedback is very cool, right? State space, but it does involve some mathematical skills, okay? But that's really the state art. Again, full state feedback is the industry state art. Of course, it does not mean this like, you know, it does not mean this like PID is dying. No, PID is not dying, okay? PID is really for time insensitive applications. You can name it, right? Let's say thermostat, your air conditioner. In the summertime, I you know, in the summertime, I don't think I talked to you. I changed my air conditioner. It cost me almost $10,000 entire AC in my house. So it's really, you know, it's really costly, and they use PID there, okay? Why air conditioning use PID? Because air conditioning is not time sensitive. You know, I mean, it's okay. Take like a minute to get temperature raised to like your desire, okay? Oh, probably 10 minutes. It's fine. However, for some time sensitive applications, people have to use this. Why we have used this? Because the full feedback actually considering closely your settling time, considering closely overshoot, which is very hard for PID to satisfy. Remember you did lab 3, right? You know, I believe some groups still struggle. Man, that's really hard. Just get a couple of coefficients and take forever, you know. And PID tuning is really a concern. Although you don't do any math there, okay? But the tune the PID take forever. It's still probably not optimal. You never know. Is really optimal? Probably not. I mean, is really problem there? Is okay? Probably not too bad. As long as your certain time is not really a big concern, right? You know, I mean, who cares? As long as you eventually go there, okay? Right? And for like time sensitive applications, And the full state feedback is the way to go. Right? I mean, so why full state feedback able to do the magic and to achieve time sensitive is because this here, look. And that's your starting point. You want to make sure your control matching their setting time. Anyone can give me some example what this time sensitive applications? What's potential applications? Anyone give me some examples?
Like the corrective driving that new cars have to keep them inside the lanes. You definitely want to have time control on that.
Yeah, thank you, Jackson. That's awesome. That's a great thought. And Jackson said self-driving. Yes, big deal, right? You know a big deal, right? It's actually in the West Coast, some state has already implemented self-driving car. I mean, I heard in San Francisco, or I know Connor. Connor, you're from Arizona, right?
Yes, I am.
Yeah, in Arizona, Phoenix, Arizona, right, Connor?
Yes.
Yeah, in Phoenix, I think they're also piloting the self-driving already. I mean, this is back to a few years ago. Right now in Tesla, right? Tesla, the new Tesla car is very self-driving actually. I mean, it's already happening. It's not something we're dreaming back 2 years ago, right? People say, no, I don't trust it. I don't think so. No, people are already happening. It's happening every single day, and because you take the Uber, right? Uber, I mean nowadays a lot of like Uber, Tesla. Alrighty, so what you learned for our class, hopefully I gave you enough at least introductions, right? Oh yeah, GM, right? Paul, right? You see, GM Cruise, yeah, GM Cruise, they already self-driverless car, right? This is nothing we dream. It's already happening. So all these cars implementing this thing called state space-based control. Although they do not use full feedback, I'll tell you, but that's really the starting point to learn the entire story here. And they mostly use, like, for example, MPC, okay? We will do one last lab 6. MPC. And this really, MPC is called Model Predictive Control. In short, MPC. So the model predictive control is really useful for everyone in the industry because it try to know every single detail of your so-called plant or your car plant, right? Your plant is your car, right? So here your car, for your engine, your electrical like motors, right? So I mean, in the back old days, people only become lazy, right? They say, look, I don't want to model everything. I just use PID. Just tune the P, I, and D. But people say, no, that's not really enough. Because PID, you tune the P, the I, D, and it okay for this scenario, but if you change scenario, it doesn't work anymore. Also, it's very hard to satisfy settling time very well because it's not considered in your model. You just really just mess around. Alrighty, hopefully I can convince you this state space model is very useful, okay? And it's really state art, okay? And that's really the high tech job here, okay? I'm not sure you can your first job high tech, probably 4 or 5 years later, okay? You jump to a high tech job, and they use this kind of like MPC, right? Use LQR. We will talk soon as well. Linear quadratic regulator. So this is really the very simple one, right? Full state feedback. You show you even saw by hand, okay? I mean, this is fundamental to understand stuff. A little bit more advanced called LQR, right? Even the state art MPC, okay? hopefully you get all the stuff, you mess around a little bit in your class, okay? Right, so it's it's cool, right? You can guarantee certain time, guarantee overshoot, which is very hard to do in PID, okay? You all feel it. It's pretty struggle to get PID very well tuned, okay? All right, so this step number 1, okay? Once you get the e to omega n, plug back, so you can get their characteristics equation, okay? And you say, oh, this second order, that's not cool. My system must be like a third order, fifth order, I mean, it could be okay. In lab 5, we model like a simulation, pretty not very complex, reasonably complex system. Okay, Stephen come here. Right. So high order just get another pose, right? Get other pose, and you see, I don't know how get other pose. What's the number? I just like imagine it, or just pick something on my own. Yes, you are. This like the third pole, fourth pole here is I'll give you some rule here, probably 10 times the real numbers of this your system pole. Let's say your system pole minus 10, right? And this is S1 probably minus 100, S2 probably minus 1000. You see, really? Is that like that experience based? I mean, at least so far, at least of full feedback. But for LQR as well as MPC, you don't need that. Okay, you don't need that. But for full feedback, you need it. All right, step number 1. Hopefully, you convince you useful, right? I mean, also you understand. Okay. Anyone have questions for step number 1? Anyone questions? Step number 1. All right, let's move to step number 2. Step number 2 is, after we getting desired characteristic equation, right? We want to match to control system. The goal here is to solve K here, okay? Solve K here. So how come? That doesn't make sense to me, right? I mean, how I can solve K just by desired characteristic equation? Yes, I mean, you can solve your control system characteristic equation, right? As long as you solve control characteristic equation, then you can just match it, right? By matching it, you can solve K, right? Because we know the control gain is K, right? K1, K2, K3, K4. We know PID we call KP, KI, KD, right? But this for like a state space-based control here, we don't call KP, KI, KD anymore. And we don't need it anymore because there is no PID, right? It's not PID. It's called full state feedback. We call K1, K2, K3, K4, K5, K3, maybe K100 for large system. But typically like a K5, K6, that's probably enough, right? I mean, this K here, make a guess. If there are 5 Ks, how many order system is solving? I tell you there's 5 gains here. How many order system is solving here? Anyone want to make a guess here? Five Ks, K1 to K5. I'll ask you how many order system?
6 order system.
Oh, 6 order, really? Why 6 order?
Because it's one more than the gain.
Oh, one more than the gain, right? Really? Let's look at the example here, okay? I expect you to, I can briefly explain to the example here, right? And I rely on you to probably, I'm not sure today we have enough time to go through the example, but hopefully I have a little time here, okay? But let's see. What's the order system here? For the 3x3 matrix. How many order? 3x3 matrix?
Third order.
Third order, great. And 3x3 matrix, right? So from K1 to K3, right?
So it's the same. You have as many gain values as the order of the system.
That's correct. You can see 5 again here. I mean, that's 5 order system. And then on then this one here on trans function denominator, and denominator is second order, third order. Here you 5 here again. You 5 here, 5Ks. 5K here is on trans function denominator is well, how many orders denominator? 5K here. From K1 to K5. So the denominator is from S5 or S4 here. Denominator should be from S5, right? To S4 to S3. Make sense to you, Paul?
Yes.
Some like let's say A, okay? And this is your how many order system? And by the way, this matrix for 5 from K1 to K5, the matrix should be 2 by 2, 3 by 3, 4 by 4, 5 by 5, 6 by 6. What's the answer? Matrix, A matrix. A matrix should be what's like how many row, how many column?
Be a 5 by 1.
5 by 1 or 5 by
Is it a square matrix? 5 by 5?
yes, absolutely. Thank you. Listen to you. Yeah, 5 by 5. Okay. So as long as you don't need to know anything else. As long as no K here. Oh look, as a house inversely. If you know A matrix is like 5, right? How many K you should have? How many K you should have? If 5 by 5 matrix A, and the K should be from K1 to
K5.
yes, absolutely. All right. So here is now this is the important thing. Okay. So you see your control system characteristic equation is this formula. You see how come you get this formula? I mean, you probably don't have to know. I mean, yes. I mean, I can explain to you a little bit next Monday, right? I mean, you just remember that, okay? I mean, this actually chapter 3 we talk about like from from state space to trans function. We did not do in class practice. I think we do probably next Tuesday a little bit practice, okay? So here is from this like given A matrix, B matrix, given A, B matrix, or C, D, right? You can calculate trans function, right? Remember, chapter 3, okay? Sorry, that bracket, okay? So you can derive it. There are characteristic equation, which is of underlying control system is determinant Si minus A minus BK. Again, characteristic equation is in the trans function. It should be characteristic equation, right? Should be numerator or denominator. Should be there's here space of the trans function. Tell me this. What's the answer here? Numerator, denominator. Numerator, denominator. Who want volunteer? Who want to volunteer here? Anyone volunteer here? Anyone?
What is it? What is it you're asking?
Characteristic equation should be numerator or denominator certain function. Let me guess. Just A, right? A and B, right? Yeah. Denominator, right? Yeah. Right. Awesome. Awesome. Thank you, Ken. Right. Thank you, Ken. Right. Yeah. Awesome. Thank you. Right. I mean, you see, Kim already telling us. Kim already telling us the denominator. Great. The denominator certain function called characteristic equation. Okay. You actually all see here, right? Look. See. Right. That's the denominator here, right? We're familiar from based on the review session, right? Alrighty. So here is, so we know the current equation, right? It's denominator, right? I mean, we know this formula, okay? You see where the formula from? Really, it is, based on this like chapter 3 from the state space to calculate certain functions, okay? All right, pretend you are convinced this is formula. So I is identity matrix, K is this K here, right? You know A, you know B, you calculate determinant, you can calculate their state space. Sorry, you can calculate their characteristic equation. And let's say for second order system, this should be S squared. So here for phase variable only, right? Let's see for phase variable. So this is a phase variable matrix, right? So what's the like what it looks like phase variable? As the first row and the second row, the third row, and last row, right? For phase variable, is last row is non-zero, okay? The K is also the control gain is also the last row, okay? Actually, so we can draw flow diagram. You can make a very clear should be last row, okay? So here, just a small quiz for control. For control mechanical, which row is for control mechanical, which row is non-zero? Small quiz. I don't know. We know phase variable last row, right? Control mechanical.
Last row.
Huh?
Is it last row?
Ah, really, Ibrahim? Really? We know phase variable is last row, right? Remember? For control.
Yeah, maybe it's. Yeah, I think I'm.
It's the
mixed
first
between
row
them.
is
It's the
non-zero.
first row. Yeah.
Yeah, thank you guys. Thank you, appreciate it. Yes, first row, right? Thank you. Yeah. See, this stuff all tied together, all tied together. Yes. So the phase variable, right? If phase variable form like this, okay? Control mechanical will be this stuff will be on top. It's still there, right? But it's on top, not on bottom, okay? Right. So you know the A minus BK matrix, right? And you plug as the identity matrix there, can determinant, you got this. This phase variable example, right? But for other different type stuff, you have to calculate, okay? So here, notice here. So this AN plus KN is last, which is last column, right? A0 plus KY is on first column. So you say this one here. So you match coefficient. So your desired curve equation match controller curve equation, okay? Your desired curve equation for second order is this. And for controller type is this. You obviously say, oh, look, this one here should equal this one, right? And then you can match that, right? You can solve K1 is this, K2 is this. So you got the idea, guys? So you got the idea? These are desired. These are controller. And you simply can match it, okay? You simply can match it. And you can solve K1, K2. And so here is, if it is, like a phase variable, you already know this the last columns, which is corresponding to first Sn minus 1, okay? Your first column it considers this just a constant. And you already know it. And so you, as long as you know A minus BK matrix, right? You solve A minus BK, right? And then you can plug a coefficient here, okay? And they just solve this K1 to K2 and to K3, K4, so on and so forth, okay? But if it is not phase variable, you have to calculate this determinant by yourself. If not calculate determinant by yourself, you just randomly plug number there, you get it wrong, okay? The K1, K2 is messed up. It's not the real answer. But only for phase variable, it's very decently. For the K1, Kn is K1, Kn here, okay? Is already fixed. Of course, you still able to just plug all this K minus BK there, manually calculate determinant. You got this stuff here, okay? So we know this one corresponds last column. This from first column. You know it, right? But actually, you can calculate by hand, okay? And this arithmetic, some students are always confused. I mean, if for let's say control mechanical, can I just plug like here, like this one here? No, you cannot, unfortunately. Pretend control mechanical here. This is A0 plus K1 here, and AM minus 1 plus Kn here. Can use your like controller curve equation just like this one here? No, sorry. You have to calculate it by yourself. I mean, it's hard to do. I don't think so. I mean, usually the second order, third order determinant is not hard to do, right? So, but for high order, you can do by MATLAB, okay? Alrighty, so actually I put this note here. Note 1, note 2, okay? Note 1 here is for 2x2 matrix. You can easily got this 2x2 matrix, right? Stuff, right? But for high order 3x3, 4x4, 5x5, what you can do? You have to create this like S1, S2, S3 literally by yourself. Let's say you follow by 10 time rule, right? Let's say this is your system pole here. And your S1 from -100, S2 from -1000, S3 from -10,000. I just plug a number there and see whether it's okay. And do some simulation. It's okay and also okay. If okay, you're good luck. Not okay, you change around a little bit. Usually it's fairly okay. Like 10 time or 100 time rule is fairly okay. Why? It's because it's faster. I mean, the real term, right? Remember, real term contributing your damping, right? And this imagined term contribute to oscillation. Okay, remember? We usually just give real pole here, real pole, not complex pole here. Even your system pole is under damping. Your S1, S2, S3 is still real pole here. Make sure we can converging very fast. All right. The second node I gave to you. The second node is really give to you here is I'll tell you that phase variable only, right? And we call shortcut. I mean, if you have phase variable, look, I have phase variable, right? I know A matrix, right? Sorry. I know A matrix, I know, right? You can derive A matrix based on the chapter 3, based on topic 3, you can derive mechanical system A matrix, right? Or circle A matrix. You plug K1, K2, K3 there, right? Ah, so beautiful. I will formulate a phase variable. Yeah, I'm done, right? Yeah, it's done here, right? You just like you don't calculate determinant. You just apply last column here, the first column here. Okay. Unfortunately, if you formulate like a formulation like a control mechanical, right, or parallel or cascade, you cannot use this anymore. You have to calculate it from scratch. Clear, everyone? So this one tell this one here. If phase variable, you have shortcut. Good luck. But if no phase variable, sorry, calculate determinant. Alrighty, so summarize. Step number 1, this is most important. Someone feel a little hard to understand, so I give a summary here, okay? Hopefully you understand it. Step number 1, obtain desired curve equation. Step number 2, magic coefficient. Just be careful for magic coefficient for controller curve equation. You want to, if phase variable, good luck, right? Just literally put here. If not phase variable, calculate determinant. It's hard, yeah. I mean, for 5x5 matrix, it's hard. I mean, you're probably not using any like hand-based calculation. Just through the MATLAB, right? You can MATLAB give you like a symbolic tool, right? Remember you learn feedback at level 4, right? Your feedback level 4 is really about this symbolic calculation stuff, right? So there, right? I mean, calculate determinant, it give you literally quickly. You can know your system like a curve, your controller, right? Your controller curve equation. Alrighty, so we have 3 minutes. So we don't have enough time to go to the example here. This example here, okay? I mean, so the example here, I already give you a poll, right? I mean, you just literally go through a little bit. So we want to design a system to place the poles in this here, okay? Yeah, 3 poles here, right? That's desired poles. You say, oh no. Dao Zhang said step number 1 to calculate your desired curve equation like this. Why giving poles? I'm confused. I mean, you know, as long as no poles, you can calculate your curve equation, right? How? It's just s minus s1, s minus s2, s minus s3, s minus 4, right? Just get them together, right? Multiply it. Multiply all the poles, and you get the desired curve equation, right? Once you get desired curve equation, right? In the flow diagram, right? In the flow diagram, and based on flow diagram, you can draw the A matrix, right? Remember, we spent a long time, even in test 1, we'll go through this get A matrix from this, right? Get A matrix there, and it got A minus BK, right? If it's variable, if it fits variable, and right, let's say here, A minus BK here, so look, fits variable, right? You see A minus BK. You plug A minus BK there, and you match coefficient. So this is desired curve equation here, and this is your, this radiativity is your, this radiativity is your K1, K2, K3, just match it, see? Fitting power 9 equal to 5 plus K3. Why? Because last row here. Remember, change the sign here, okay? And this thing here is the 136 so equal to this one here, the second column. And the last 413 here is equal to the first. So sorry, equal to the first one, K1. See that? It's done. K1, K3 is done, right? You solve everything. See how easy? Life is beautiful, right? Yeah, see it's done, right? Right? Anyone have questions? Tuesday, on Monday, we can do another example in class, but please go to the example by yourself, okay? I mean, so I don't think it's hard based on the flow diagram, right? You can draw state space, we all know it, and from A minus BK, which fits variable, and match coefficient. And the tricky part is the steps. I mean, I already summarized for you here, okay? Just follow the step here, and hopefully it makes sense to you. Alrighty, so briefly, your test-wise. Our test is, so next Wednesday. So should be in class. So we will like test mostly state space modeling, circuit, right? Mechanical state space. Please carefully go through this mechanical state space, circuit state space, and you're welcome to the cheat sheet. I mean, that's fine. So just go through the homework, right? Class engagement and lecture notes. I will give you like a study guide, probably some like some simple example questions, and I will probably do another review. Again, we cannot spend the entire lab to review, okay? But I will spend some time to review in the lab sessions. Is okay, everyone?
Yes, sir. Just to make sure, could we potentially get that topics list and practice test like by this weekend? Is that, if that's possible? I know you'll be driving, so I don't want to put too much pressure on you, but if that's possible.
Of course, I will do. That's no concern at all. Okay, that's no concern. Yes, we do that. Yes.
Awesome, thank you.
Perfect. Yeah, Kathleen asked, which study for, right? I mean, there's a couple. I'll probably make it more clear in study guide here. But in give here, right? Let's go back here. So class engagement here, and in the before, actually, I asked students to submitting this class engagement almost like homework. I think because that's probably too much. So this semester I will not ask you to submit. I mean, actually, some students already submit, although it's not part of curriculum. But thank you, I appreciate that. Okay, let's say class gaming 2, right? Let's class gaming 2. Okay, hold a second. Let me see. Yeah, see this one here, this one here, this one here, this one there. Yeah, this one here. I mean, this one here, right? I mean, for this one, we did not do practice. I think for a solution already online there. Okay, so you go to class in grade 3. But you know what? Next Tuesday I will give you this from this stuff. I'll give you a little example in the class. But again, in the test, I will not ask you to translate like a 5x5 matrix to transfer function. That probably no, that's too hard. I don't think that's we want to do that. Okay, but I mean, as a practice, you still want to do that. I mean, let's class in 3. So the solution here. You go to all example here. 1 second. You see this example here, the solutions here. I mean, please go through it. Okay, I don't think it's hard, right? The class 3. Okay, class engagement 2 also related. Let's look at class engagement 2. Okay, and this class engagement very important. Just be very cautiously study hard on class engagement homework, and as well as the lecture notes, right? I mean, so I can solve hard questions. I just cannot solve the lecture notes questions. Okay, please solve the lecture notes questions. Okay, right? You see this one here as well, right? See this one, this class 2, class 3. Look, mechanical version. Okay, I mean this is from transfer function, right? Right? I mean this one in state space, and from state space through to transfer function as well, right? All right. So here is class 2, class 3. They all strongly relevant. Let me see class 4. Class 4. Let me see. Class 4 is yeah. This one is test 1. Okay. I mean this one as well. Okay. This question 4. This one as well. I mean, yeah, this one as well. Okay. So. This second test is almost the last test. I mean, we have final exam by the way, but you know, but we had no exam 3 anymore. Okay, we have final exam, but we had no exam 3 anymore. So we had class 2, class 3, class 4. Okay, class 5. I don't think related. I don't think so. Let me see. I don't think so. You know, this is nothing to do with this test. Class 2, class 3, class engagement 4. Okay. Class engagement 1 also related, by the way, right? So actually, this class engagement is dedicated for this test 2, by the way. I mean, pretty much. All the class engagement is because some students find a little bit challenging to do this state space modeling, right? So this we prepared a 4 class engagement for you. So you should have enough practice because you can see the solutions, okay? As well as homework, as well as lecture notes. If you do well, right? Again, this is accumulative. So some under damping, critical damping, saturation time, overshoot. Also this like how the curve looks like. You know, the curve looks like under damping, critical damping. I mean, you also want to study as well, right? And they're not taking a very big percentage, but still there. Okay, don't lose points. And also here is, you know, if you give you a flow diagram, draw state space, give you like a state space, draw flow diagram, all this stuff, you probably not want to forget. And that again, they do not take a big percentage, but they do on they're a little bit on the exam. Okay, it's just like because some students, the reason here is some students not quite able to do this stuff. If everything about the state space modeling, some students may get a very low score, okay, and pretty very low. You know? I mean, so just make a little balance. I mean, we still have some maybe like basic stuff there, okay, but again, this state space modeling take quite a percentage on the second test. Any other question for test? And
So
then-
to make sure, class engagement 1, 2, 3, 4 for now. Before we get the topics list, so it's gonna be 1, 2, 3, 4. Lecture notes, topic 1, topics 3 and 4, and then homework 2 for now.
Yes, but again, great question. Again, it's cumulative. So like a draw like a functional block diagram, just like a topic 1 stuff still there. So like
Understood. Okay.
yeah, still there. So like some test 1 questions you probably still able to say, okay. I mean, not identical question though. I mean, similar questions. You're still able to say in this test. That's considered a bit easy, but yes, we're also doing stuff from test 1. So we are also doing stuff from test 1 on test 2. I mean, not identical though. I mean, related. I mean, so let's say draw a block diagram on there, right? You probably draw another block diagram, okay? And so make sure someone again probably not everyone equally like. I mean, yeah. Let me see. 1 second. I don't want to disturb anyone, but probably my Zoom isn't let me hear anything. Could I get a link to recording? Yes, of course. Sure. Adam had a hard time. Let me see. Adam had a hard time to hear. Okay. All right. Yes. So you get recording. Okay. So probably not everyone equally like. I mean, why accumulative? I mean, can we just like a state space modeling? Yes, I can. Right. That probably causes some challenge for some students. Just like have a hard time get a decent score here because not everyone very fluent on state space modeling yet. So we make sure get a reasonable score there. Okay. So Catherine, makes sense to you? So test 1 related question similar, right? But still there. Okay. We just make sure clear everyone. So again, it's accumulative, but this state space modeling will take quite a big percentage. Okay. Again, I mean, just study closely. Okay. Anyone have question for test? No? All right. I will give you the study topic, and so you can just study closely to it, and so we can start from there. Without further ado, please stop by my office and ask questions, and I'll be there on like a Thursday afternoon time as well as Friday, and but I will come back to South Carolina on Friday night, but I'll drive back to on Sunday as well. Okay, so so you will not miss me in morning class. Alrighty, without further ado, right? I'm sorry they will delayed for you because we talk about test here, but regardless, I will see you next time. You're welcome to stay, and if you want to ask me questions. Adam, still can hear me or you cannot hear me, Adam?
Here, can you hear me?
I can hear you.
I don't like that. Why can't I hear?
Yeah. I mean, what you can do, Right.
President.
Yes, Gabe. Is anyone coming today or no one coming?
Nobody came today.
Thank you, Gabe.
All right, bye.
Alrighty, sure. So any other question, Gabe? No questions?
No question.
Alrighty, thank you. I appreciate you coming here today, okay? Right, and yeah, I will then see you then, okay?
All right, bye.
Bye.